You ever wonder what's actually powering these giant AI models we hear about all the time, like Gemini? Well, it's definitely not your standard computer chip. Nope. It's something way more specialized, a piece of hardware that's been custom built from the ground up just for AI. So today, let's pull back the curtain and see what's really going on under the hood. So what's the big deal, right? I mean, why can't we just throw a bunch of regular computers at the problem? The answer is, well, it's kind of simple, but also just mind-bogglingly complex. At the end of the day, it all comes down to the sheer unbelievable scale of the work that these AI models have to do. Yeah, that's right. When you strip everything else away, modern AI is really just built on one single type of math. But it's being done trillions of times, every single second. And, to handle a workload like that, you just can't use a jack-of-all-trades tool. You need a specialist, a real pro. And this is exactly what brings us to the core challenge, the very reason Google created the Tensor Processing Unit, or TPU. We are talking about a math problem that is basically endless. It demanded a specialist, a machine designed for one job and one job only. And that one job, it's matrix multiplication. Now, here's the really important part. This kind of math needs a huge amount of calculation for what's actually a pretty small amount of data. This is what engineers call being compute-bound. Basically, the bottleneck isn't moving data around, it's the raw horsepower needed to do the math. And that, right there, makes it the absolute perfect problem for a piece of dedicated, specialized hardware. And that specialized hardware, that's the TPU. Honestly, the best way to wrap your head around a TPU is to think of it like a hyper-specialized factory. This isn't some general-purpose workshop that can build anything. Nope, it's an assembly line, built from the ground up to do just one thing. Churn out matrix multiplication at a totally insane scale and speed. Yeah, this quote really nails it. See, it's not just about the part that does the math. It's about the whole system. You've got this specialized engine, the matrix core, and it's physically attached to its own big stack of super fast memory. The two are totally inseparable if you want to get maximum performance. All right, so how about we take a little tour of this factory floor? To really get how a TPU pulls off its incredible speed, we've got to look at its three main parts, and more importantly, how they all work together like a perfectly oiled machine. Okay, first up is the high bandwidth memory, or HBM. Just think of this as the factory's gigantic warehouse. And when I say gigantic, I mean it. A single TPU V5P chip has 96 gigs of this stuff. This is where all the data is stored. All the model weights, all the parameters, everything. But, you don't work directly out of a giant warehouse, right? That's not efficient. So data gets moved to a smaller, way more accessible spot. And that's the VMEM, or vector memory. Now, it's tiny compared to the HBM warehouse, but think of it as the workbench that's sitting right next to the assembly line. The connection to that line, the bandwidth, is just ridiculously fast. And here it is, the main event, the MXU, the matrix multiply unit. This is the assembly line. It uses this really clever design called a systolic array to just tear through matrix math. The best way to picture it is like a grid of thousands and thousands of tiny little calculators all working together in perfect rhythm, in perfect sync, to pump out hundreds of trillions of calculations every single second. It's just wild. So when you put this all together, what you get is this perfectly choreographed dance of data. Chunks of data are pulled from the big HBM warehouse. They're placed on the super fast VMEM workbench right at the exact moment the MXU assembly line is ready for them. This whole pipeline system makes sure that the powerful MXU is never, ever sitting around waiting for work. It's always being fed, always running at full throttle. But here's the catch. Modern AI models are just so mind-bogglingly huge that one factory, well, it isn't going to cut it. You don't just need a factory, you need an entire factory town. So let's zoom out and see how these individual TPU chips are all wired together to build one of the most powerful supercomputers in the world. And this right here is a really key difference between how TPUs work and how their GPU cousins work. See, TPUs are connected using a direct nearest neighbor link. They call it the ICI network. The best analogy is a perfect city grid, where every factory has a direct road to the factories right next to it. It's simple, it's clean, and it's super scalable. GPUs, on the other hand, tend to use something called a switched fabric. Think of that more like a national highway system, with all these complex interchanges designed to get you from any point to any other point. It's really flexible for sure, but it's also way more expensive and complicated to build out. And when I say scalable, I am not kidding.
A single Google TPU V5P superpod, it links together 8,960 of these chips. Let that sink in. This isn't just a rack full of computers. It's a single, massive, cohesive supercomputer with every single one of those chips working together on one giant problem. But of course, even with a supercomputer this powerful, you just can't escape the laws of physics. There's always a bottleneck. Your performance is always limited by the slowest part of your system. And in these giant factory towns, the biggest speed bump isn't the factories themselves, it's the roads that connect them.
Okay, this chart says it all. See that giant bar on the left? That's the speed of moving data on the chip itself. We're talking almost 2.5 terabytes a second. Insane. But now, look at the next bar. That's moving data to the chip right next door. The speed just plummets, drops by over 95%. And then, moving it to a whole different server, it's just a tiny little sliver of the original speed. That is the bottleneck. Here's a great way to think about it. Moving data on the chip is like a fire hose, just a massive torrent of data. Going from one chip to its neighbor, that's a garden hose. And going from one server to another, well, that's a dripping faucet. And figuring out how to manage these bottlenecks, how to work around this, is honestly the single biggest challenge in building these AI supercomputers. So, okay, why does any of this tech jargon matter to you? Well, because this stuff is already all around you, every single day. This is the engine that trains Google's biggest AI models, like Gemini. It's what's working behind the scenes to give you those instant results in Google Search and Google Translate. And if you're a developer, this exact same world-class power is right there for you to use through Google Cloud. All right, so if you're going to remember just one thing from all of this, let it be this. The real secret to building these incredible machines, it's not just about having the fastest chip. That's it right there. For these AI supercomputers, raw speed is completely useless if your data is stuck in traffic. I mean, you can have the fastest processor on the planet, but if it's just sitting there twiddling its thumbs waiting for data, that speed means absolutely nothing. The real genius of the TPU system is that it's just as much about moving data efficiently as it is about the number crunching itself. Yeah, it's this incredibly delicate balancing act. The central challenge is figuring out how to balance that raw computation with communication. You have to perfectly choreograph how all that information flows through those different sized pipes. The fire hose, the garden hose, the dripping faucet, to make sure the entire system is humming along without any traffic jams. And that really leaves us with a fascinating question for the future. As AI just keeps getting bigger and bigger, the next huge breakthrough, it might not be a faster chip. It might be a smarter way to connect them. The next revolution is probably going to come from inventing smarter, faster, and way more efficient ways to link tens of thousands of these things together. So what will that new city grid look like? That's got to be one of the most exciting questions in all of tech right now.